So before we actually move on to greedy algorithms, I just wanted to discuss what is this optimization problems, because some of the like terminology that will be used to describe the greedy and dynamic programming solutions would be using this terminology, which is all of these design techniques kind of stem from the field of mathematics, specifically from optimization problems. So they are more mathematical in nature compared to like more computer sciencey. So because they were derived from the field of maths. So essentially, when we talk about optimization problem, so what we are working with is the problem of finding the best solution from all feasible solutions, which is you could have a lot of feasible solutions. And what are feasible solutions? We are just going to look at it. So like I just wanted to go deep before you can actually understand the context around what is going on. So whenever we are trying to solve a problem, there will be constraints attached to the problem. Like I'll give you an example of what a constraint is, which is like on STEPIC, when you try to solve these problems, what we do is you have a threshold of 30 seconds per test case, which means that if your program runs for more than 30 seconds, you are like going to get a 0 because it's going to give you a time limit exceeded error. So that is essentially a constraint that is attached to a problem, which is like an example is like if you are creating a mapping application, you might ask a person to go from place A to B in 10 hours, which is let's say a person wants to travel from between two destinations, and you give a constraint to the problem, which is they have to complete this in 10 hours. That is basically like adding constraints to a problem. And whenever we are talking about like adding constraints to a problem, these constraints will either allow you to minimize or maximize an objective function, which is essentially what we are doing is like there's a direct relationship between constraint and an objective function, where like let's say if we specify that a person needs to go into A to B in 10 hours, what we are trying to do is our objective function inherently is essentially to minimize the time so that a person can go from point A to point B. Now, what is a feasible solution? A feasible solution is a set of values for the decision variables that satisfies all of the constraints in an optimization problem. So let's say if a person has to go from A to B, there might be a lot of solutions, right? And we gave a person less than 10 hours, like we need a path from A to B so that a person takes like less than 10 hours to reach the point B. There could be a lot of solutions, which is maybe the person is traveling from A to C first and then C to B, where they might take like 4 hours for this, another one like maybe 6 hours for this. So they satisfy this inequality, like which is, it should be like less than 10 hours. That's what I'm trying to state here. Or they could be something like they go from A to D and then to B, where from A to D they take 1 hour, and the other D to B they take like 8 hours, and so on. So all possible solutions that satisfy this inequality, which is, let's say a person takes like 9 hours, 8 hours, 7 hours, 7.5 hours, they take different paths to reach to that to the final destination. All of those are feasible solutions, which is it is satisfying all the constraints in the optimization problem. Like what would not be a feasible solution would be like, let's say if a person goes from A to Z, A to C via Z, and they are taking 11 hours, since that is not a feasible solution. That is not a feasible solution because it is not satisfying a particular constraint. So in order to like solve these optimization problem, you might generate a lot of feasible solutions. Now the thing is, like whenever you are designing these particular problems, there is like you might take some steps that would allow you to generate these feasible solutions. Okay, one or more feasible solution. So what is an optimal solution? So an optimal solution is a feasible solution where the objective function reaches its maximum or minimum value depending on what you're trying to do. So essentially, when we talk about optimal solutions, there are two different variants. One is a globally optimal solution and the other one is a locally optimal solution. So globally optimal solution is one where there are no other feasible solutions with a better objective function values, which is essentially like, let's say if there are a lot of paths that a person can take from A to C, such that the minimum to minimum path that one can take is 4 hours, while the maximum to maximum like hours that a person can take from A to C is 10 hours, because that is the threshold of our constraint. A globally optimal one would always yield the best to best of everything, which is in this case 4 hours. Okay, and a locally optimal one is one where there are no other feasible solutions in the vicinity which are better than the objective function values, which is what you can think of is like, let's say all of these are the times to reach from A to C, but depending on your algorithm design, what you might have is you might not be able to find all of these R's. You might be able to find a few of them that satisfy the inequality, and you just return one of them. So that is a correct answer because it satisfies the inequality, but it's not the best one. So essentially, that is the idea of a local optimal, which is you have a big solution space. Like for every problem, you have a large solution space, and out of all those solutions, a few of them are feasible solutions. And out of all those feasible solutions, only one of them is a global optimal, while there are several local optimal solutions. Okay, so that's basically the gist of it. And for every problem that we try to solve in an optimization problem, our goal is to generate an optimal solution. Like the ideal goal is to generate the globally optimal one, but in the real world, sometimes it's not possible to compute all sort of permutations and combinations, and we are fine with getting a locally optimal solution. So that's kind of the gist of it. When we talk about specifically greedy algorithms, they actually work in phases, and in each phase they make a decision which is based on a heuristic, or a heuristic is basically you can think of it as an attribute which allows you to take a decision. Okay, and at every step you take a local optimal. So which is in this case, like let's say if you start here for a particular problem, you might return like as you are solving the problem, you might think that you have reached the peak because you are ascending up the problem space or getting close to achieving your objective function, but you might not realize that like when you are at this peak, you might think that, oh, now we are actually going down, so we have actually found the optimal, but that might not be the global optimal because you have not completely covered the solution space. So essentially, greedy algorithms, they guarantee a local optimal but not a global optimal, which means they might not give you the best of best solutions. Okay, it's really hard to prove whether an algorithm is a global optimal or a local optimal. Like in this case, Prim's and Dijkstra's, they are going to give you like global optimal, but it's outside the scope of the course on how to determine whether it's a global or a local optimal. These are like entire PhD theses or like very difficult problems that are solved by those who are there in the field for very long. So essentially, like I'll give you a concrete example. Like let's say if I tell you, like I give you this binary search tree, and I tell you to find the largest, to write an algorithm to find the largest number in the tree. And what you do is, like, the tree is really big, so you cannot go to every node, because if you can go to every node, that means like you can just use brute force, right? So essentially, what you're going to do is you're going to solve this using a greedy approach, and what you can do is you check the node, which is the root in this case, and then what you do is, depending on whether the root is larger or either of the children are larger, you go in that direction. So essentially what would happen is, like 5 would be compared with 4 and 10. Like since 10 is the greatest element, you will keep on going towards the right hand side and take a decision to go towards that direction in the tree. Next, you have all these three numbers, this trio, and out of these 25 is the largest number, so you go towards this side of the tree and you keep on going like this path, keep on going down towards this path to return like a really large number. But essentially what you can see is we have already taken a wrong route, which is we are going towards this way, while here we have realized that the largest number in the tree was like 100 in this case. So essentially we are making decisions on which way we should approach towards in the problem space based on something that is close by, based on a heuristic here, which is out of the heuristic here is out of the three numbers, which is the largest, go in that direction. Okay, so I'm considering this might be a graph or something like that, and it could be really big, which is having a lot of nodes. So essentially this is the key idea. Another way to see this is in a two-dimensional plane here, which is it's a three-dimensional plane here. So essentially it shows you an entire problem space, and as you are solving the problem, you might go into like one of these peaks, which is like shown here, but and return that particular answer, but the global maximal might be a completely different peak, which might be in a completely different direction. So that's the gist of it. I'm going to talk to you about like a few more examples on different algorithms in the next video.